guys, welcome to our last video for Unit 5 on satellite motion. And satellite motion is maybe not the best title. We could also call this orbital motion, and we could also call it planetary motion. We're really looking at any kind of motion that involves an object orbiting around a center of mass. So we're going to look at two central questions today. Sorry, I'm starving, so I'm eating while I'm teaching. The first question we're going to look at is, how did Newton prove that gravity from the sun was the force that caused the planets to orbit? And then the second thing we're going to look at is how to calculate acceleration of an object that's orbiting, how to calculate its velocity, and how to calculate its period. So let's go back to our first question today. Newton was able to prove that the moon orbited the Earth, and that the reason why it was orbiting was due to the force of gravity. But he wanted to prove that the Earth orbiting around the sun was due to gravity. So the Earth's orbit around the sun is not circular, it's elliptical, meaning that it kind of looks like a smashed circle. Okay? So this is the orbit. And this looks a lot like uniform circular motion. And so we're going to use the principles of uniform circular motion to help us answer this question. So one thing we know about uniform circular motion is if the object doesn't have friction at play, which we're going to assume that there's no friction at play with the Earth moving around the sun, okay, no friction, that means that the net force acting on the Earth, okay, what's the net force? Well, we know that there's a force going inward here. That's the centripetal force that the sun is pulling on the Earth. There's no normal force. And there's also no friction force because it's not sitting on an object. Okay? So there's only one force at play, the centripetal force. That means that the net force on the Earth, is the centripetal force. Okay? Our net force equals our centripetal force. We know that. So how can we calculate our net force? Well, net force, or our centripetal force in this case, okay, the centripetal force of the Earth being pulled onto the sun, since it's equal to the net force, it equals mass times acceleration. Because you know how your net force is mass times acceleration? Well, if F net and Fc are the same, then we can kind of write out this formula. The centripetal force acting on the Earth is equal to the Earth's mass times the Earth's acceleration. Okay? Now, what we learned in our previous video was we learned a formula to calculate the gravitational force of an object. It was a capital G times m1 times m2 divided by radius squared. So let's go back to our central question. We know we have a formula to calculate the force that the sun is pulling on the Earth to make it go in an orbit. And we know a formula for the universal formula for gravity. So Newton wants to prove that gravity is the centripetal force. Newton wants to prove that gravity is the centripetal force that pulls the Earth around in a circle around the sun. He wants to prove this. So how would he prove this? Well, we could find out what the value is for centripetal force, and then we could find the value for our gravitational force, and we could see if they equal each other. So that's what he did. So let's start with F of C. I'm going to find the centripetal force that pulls the Earth around the sun. So we need to have the mass of the Earth times the acceleration of the Earth. So the mass of the Earth we have, it's right here. It's a number I gave to you. Okay, but acceleration of the Earth is not listed. It's not one of our givens. So we have to find it an alternate way. Well, we did learn in our centripetal force lesson that the formula for acceleration can be also shown as v squared over r. So we have radius, it's right here, it's this long number. So we have radius, but we don't have the speed. See, the speed's not listed here. However, there is another formula for speed. It is 2 times pi times the radius divided by the period. That's what t stands for. So we have period, it's right here. We have radius, right? Radius is right here. So we can find speed, and then we can find acceleration, and then we can find f of c. So we're going to start by doing velocity. So 2 times 3.14 times our radius, which is 1,000. Well, it's not 1,000. It's this really long number. All of these meters divided by our period, which is this many seconds. When I divide it, I will get 29,769.7 meters per second. And if you Google the speed of the Earth around the sun, it'll say 30,000. So we're actually really close to the Google answer. So we have velocity. So now I can plug it into this equation here. Acceleration is my velocity. Oops, that's 69.7. Square that, divide it by r, my radius, which I am also given. And I get an acceleration of 0.00592 meters per second. Okay. So I have velocity and I have acceleration. So now I can use this acceleration value to plug it in here and find my f of c. So my mass of the Earth was given right here. It's 5.972 times 10 to the 24th. And I can multiply that by my acceleration, which I just calculated, which is 0.00592 meters per second. When I multiply them, my f of c value is 3.54, if I round, times 10 to the 22nd newtons. That's a pretty big force. So I'm going to highlight that so we can see that in just a second, because our goal is to compare our centripetal force to the gravitational force and see if they're the same. So now I have to find my f of g. Okay, so we found fc, now we need to find fg. So we're going to be using this formula, the formula we learned in the last video. So g is always it's 6.673 times 10 to the negative 11. And then I'm going to multiply it by my two masses. I need to kind of scroll back to see what they are. Okay, the first mass, the sun's mass is 1.989 times 10 to the 30th. And the Earth's mass was 5.972 times 10 to the 24th. So all I'm doing is plugging in the givens, okay? I have all these givens. Divide it by my radius squared. I don't know why I put the 2 down there. It's supposed to be squared. So my radius was also given to me right here. It's that really long number, 149,597,870,700. When I divide all this together, I get 3.542 times 10 to the 22nd. So what does that number represent? That represents our f of g force. Okay, that represents the gravitational force. So we need to double check and say, hey, is this number the same as this value? And they're the same. So what does that mean? It means that the pull on the Earth towards the sun is 3.54 times 10 to the 22nd power newtons. The gravitational force between the two objects is the same number, almost the same number. So since the gravitational force between these objects is the same as the centripetal force between the two objects, we can safely say that the gravitational force is the force that causes this thing to orbit because they equal each other. Yay! So that's part one. Part two is going to be learning how to calculate acceleration of an object, velocity of an object, and period of an object that's orbiting. Okay? What's cool about this is you only need two pieces of information to find out those three things. So let's go back to what we learned about our formulas. We know that f of net equals m over a. We know that when an object is orbiting, okay, in circular motion, that f of net equals f of c. So we have this formula. F of c is mass times acceleration. Now this is of the orbiting object, okay? So the mass of the orbiting object and the acceleration of the orbiting object is the centripetal force, okay? We also know from our previous thing that your centripetal force is going to be the same as the gravitational force pulling an object when you're orbiting. So we know that our gravitational force formula is this, and our centripetal force formula is this. So if f of c, right here, equals f of g, that means these two formulas equal each other. So we can make one big formula. We can take this formula right here and say g times m1 times m2 over radius squared equals this formula. M of the orbiting object times a of the orbiting object. And it's important that you label those. M1 and M2 just stand for, one stands for the orbiting object, and 2 stands for the central, that's the word I'm thinking of, the central object that's it's being orbited around. So when you have something that's orbiting, you can have these two formulas equal each other, which is so great. There's also something we can do to simplify this. Okay, so remember in algebra, if you have something on one side and something on the other side, you can cancel them out. So this is the mass of the orbiting object times the acceleration of the orbiting object. Well, on the other side, I also have mass of the orbiting object being multiplied by other things. So I can actually cancel out the mass of my orbiting object from either side so that my new formula is gravitation times mass of 2. Mass of 2 is your central object that the thing is orbiting around. Divided by r squared will give me the acceleration of my orbiting object. Okay. So this is the formula we're going to be using now, in addition to our formula for acceleration, which we learned a while ago, and our velocity for acceleration, which we learned a while ago. So we're going to be using these three equations from now on when we're doing satellite and orbiting motion. So did I put a problem up here? Okay, here's my problem. In fact, I'm just going to copy this right here, and I'm just going to move it on down so that we can see it down here. So there's our formulas right there. Okay, and here is our problem. Okay. We want to find, I didn't copy the question down above, but it wants to find, the question asks us for acceleration, velocity, and the period of the orbiting object, okay? So here's the object, here's the central object, this is the orbiting object, okay, and it's going around in a circle, okay? So we have the mass of the planet, that's the central object, is this. So this is M2, okay, your central mass. The radius of the object is right here, so this is radius. We can solve for acceleration, velocity, and period with just these two pieces of information. So watch and learn, people. Okay, so if we use this first formula, when we're looking for acceleration of the orbiting object, we have radius, we have M2, and g is always given to us. So we can just divide these to find my acceleration. So G, you know, is always this value. You don't have to memorize it. It will be given to you. M2 I was given, it's right here, 5.82 times 10 to the 6th divided by my radius squared. Okay, and I'm going to get acceleration of my orbiting object. So here I go. Let's type it all in. And divide it. Oops, almost forgot to square. That's important. I don't know what's happening there. All right, so for acceleration, I get 8.09 times 10 to the negative 21. That's my acceleration. It's a very small acceleration. And making sure I did this right, sorry. Okay, so now I found my acceleration, ching. Now that I have acceleration over here, what can I find? Well, I have radius, so I could find my velocity. So let's do our acceleration is 8.09 times 10 to the negative 21 equals v squared we don't have, r we do have. R is 2.19 times 10 to the 8th. So how do I get v squared by itself? Well, I need to move this guy to the other side. So I need to multiply both sides by 2.19 times 10 to the 8th, so I can get rid of it on the bottom. So 2.19 times 10 to the 8th times 8.09 times 10 to the negative 21 gives me this value, 1.77 times 10 to the negative 21 is v squared. That's not v. So how do you get rid of squared? Well, just take the square root. So I take that value, I plug it in my calculator to get the square root, and now velocity is 1.33 times 10 to the negative 6. So now I have acceleration and I have velocity. Now that I have velocity and radius, I can find my period. So I have velocity, so 1.33 times 10 to the negative 6 equals 2 pi. 1 second, please. Close the door. Radius is 2.19 times 10 to the 8th. 2.19 times 10 to the 8th divided by my t. T isn't time, it's period. So I'm trying to solve for t. How do you get t? Well, it's on the bottom, so I need to put it on the top. So multiply both sides by t. Okay. Now t is gone away. We don't have t anymore. Yay. But we have t times this value. Well, we don't want this value on this side, so let's divide. So it's gone. So now this is gone. So t equals this value. So I do 2 times 3.14 times 2.19. Do your second e button, 10. Time it to the 8th power, and then I divide by 1.33 second e to the negative 6. And so my period now is 1.03 times 10 to the 15. Okay, and remember, this is how many seconds it takes to make one rotation. So it's probably going to be a really big number because it's in seconds. Okay, and that's it for your 5.4 video. You guys have a great day.